Let's try to solve this problem here. So we have boxes A and B, and they are in contact on a horizontal and frictionless surface as shown in the figure. So here we have box A, we have box B, and they are both on a horizontal frictionless surface, and block A and block B, they are in contact, they are touching each other. Okay, so box A here has a mass of 20 kg. Let's label it. This box A here is 20 kg, and box B here has mass of 5 kg. So we label 5 kg. A horizontal force of 100 Newton is exerted on box A. So this force here, it's pushing on box A over here, and it has a magnitude of 100 Newton. Now they ask what is the magnitude of the force that box A exerts on box B. So box B will be experiencing the force, and that force will be exerted by box A. So we should expect something that we want to determine over here. So let's don't focus too much on what they are asking. Let's focus more on trying to understand the situation. So in order to understand the situation, in chapter 4 forces, we use free body diagram to illustrate all the forces acting on an object. So since we have two objects over here, we'll be drawing two free body diagram. First free body diagram will be on body A, second free body diagram will be on body B. So let's draw the free body diagram from body A. So we'll use a dot to represent this body A, boxes A. Okay, it's not body, it's boxes A over here. So after that, we'll have an axis. So since this object has a possibility to move in the left-right dimension, we'll put our axis this way, y and x. Now let's try to ask ourselves the 5 questions in order to determine what are the forces acting on box A. Okay, so the first question, does this box has mass, does this box has mass or not? Yes, it's made of something, it's 20 kg. So because it has mass, you should expect weight, and weight should be pointing down if our earth is beneath. Next question, is this box A here attached to any strings, ropes, or cables of such? Well, you don't see any ropes, you don't see any cables, so no tension. Next question, is there any force being explicitly mentioned or shown in the diagram? Yes, they say you have a horizontal force of 100 Newton and it's exerted on box A. So this free body diagram of body A, of box A here, is to illustrate all the force exerted on A, right? So this will fit the description because it's exerted on A. A is experiencing this 100 Newton over here. So we should include this one in the free body diagram as well. And since it's pointing to the right, we will follow pointing to the right, and we will call this as F. Okay, since it's an external force. Next question, the fourth question, is this box here touching any surface? Yes, the box is touching one surface. The box here is also touching another surface. So the box is touching a total of 2 surfaces. So you should expect 2 normal force being exerted on this box A over here. Let's deal with this first surface over here first. This surface here, the floor, is exerting a normal force on box A. So what is the direction of the normal force? Again, it's perpendicular to the surface. So this is the surface. Perpendicular will be something like this. Pointing up or pointing down. Again, this is exerted by the floor on box A. So the floor is supporting the box A. So the floor want to push on A, you have to push upwards, right? So normal force will be pointing upwards. So I'll point upwards. It's a bad habit of mine. You don't need to do this arrow over here. It's a bit confusing. I just leave it like this. So this one will be normal force. Okay, label it as N. Then next, we have also another surface which is between A and B. So between A and B, this force is a normal force also, but this normal force is exerted by body B on body A. Because body A is in contact with body B, therefore body A will experience a force exerted by body B. Okay, box B will push box A, in other words. Okay, so think of the situation, how to determine the normal force. Again, it's perpendicular to the surface. So perpendicular is this way, so either to the left or to the right. Now think, box B here is pushing box A. So if box B is pushing box A, it has to push this way, right? Push this way. If this way, you'll be pulling box A already. You want to push box A. So push box A have to be this way. So in that case, we know that the normal force, we have to point in this direction. Okay, now we see here we have two normal force and they are both labeled as N. So this is a very confusing situation. So in order to avoid the confusion, you should include a subscript to show clearly this net force is what net force. Is it different from this net force over here? Okay, so how are we going to label normal force or any other force? There's a good way of labeling things which can be very clear, then it avoids any confusion. It's using the phrase by what, on what. Okay, so if you look over at this normal force over here, this normal force here is exerted by the horizontal frictionless surface, or we call it the ground, or we call it the floor, is exerted by this floor on body A, right? On box A. What do I keep calling it body? Okay, it's exerted by this floor on this box, right? So it's by the floor. So if I fill in the blank, it'll be by the floor on A. So if I want to, how should I put it into notation is I'll change it to floor A. So this is how I write it. So I write it as subscript floor A. So next time when you see any free body diagram, you see two alphabets in the subscript, right? You see 1, 2 alphabet in the subscript. That means it's by something, by the first thing, on the second thing. Exerted by the floor on the box A over here. Okay, you can call it floor, you can call it ground, but since F usually we use it to represent force, right? Probably change it to ground is a better word. Let's change it to ground. So this one is by the ground on body A. So I change it to ground. Change it to G. Okay, how about this one over here? This normal force over here. This normal force here is exerted by box B on box A, right? Box B is pushing box A. Box B exerts the force. Box A experiences the force. So in this case, if you write it, it will be by B on A. So if you transform it into notation, it will be BA. By B on A. So this is how I label it, by B on A. Okay, so this is a way for us to notify to state clearly what is exerting the force, what is experiencing the force. Okay, so I think that's it for this free body diagram. So I'll clear out this part where I write all these scribbles. Oh, okay. We still have one more question. The last question is this a rough surface or not a rough surface? So we are touching two surfaces here, and there's sliding happening in this surface. So we need to take into account of the friction in this surface. Over here, you don't see any attempt to slide. You don't see any sliding happening up, down. So you don't need to take care of this surface over here. So you don't need to know this is frictionless or rough surface because you are not attempting to slide. You are not sliding in this direction. You are sliding in this direction. So look at this surface over here, and it says this surface is frictionless. So you have no friction for this situation. So that's it. That's your free body diagram for box A. Now let's move on to box B. But before we move on, let's clearly label this is for box A. Now box B. Box B, we use again a dot to represent box B, and we will label our axis in the same way as box A. So this will be Y, this will be X. Now ask ourselves the 5 questions again. Yes, this object has mass, so it has weight. So this will be weight. But since now you see this weight and this weight here, they are represented by the same symbol. So what do we need to do? We need to introduce subscript to differentiate these two different weights. So this one I'll call it weight of box B. This one I call it weight of box A. Okay. Next question, is this object here attached to any strings, ropes, cables? No, so no tension. Is this box over here being exerted with a force being stated explicitly in the question? Well, you see this 100 Newton force is exerted on box A. You don't see the arrow touching B. So this force is exerted on A, but it's not exerted on B. Okay, you look at what's happening around box B. You don't see a push exerting on B. You don't see a push exerting on B. So in that case, there's no external force for box B. So let's move on to the next question. Is this box here, box B here, is it touching any surface? Yes, it's touching two surfaces. So one of it is the frictionless surface, the floor. Another one will be this block A over here. So it's touching this box A, it's touching this surface. So there will be two normal force that we need to draw out. So let's focus on the first surface, the ground first. So we will have a normal force. Again, normal force is perpendicular to the surface. So this one should be pointing up. Okay. So pointing up, normal. Then we also have the second surface. This second surface here, this is exerted by box A on box B. So box A is on your left, right? So box A want to push box B, box A have to push this way. If this way we pull already, right? So it has to push this way. When you say normal force, it's always a push. It's never a pull. It's always a push. So push this way. So you see normal force pushing to the right. So this will also be a normal force. So now since these two normal force, they have the same symbol, we need to provide subscript to state things clearly. So for this one, this is exerted by the floor on box B. The floor is the one exerting the force. The body B here, the box B here is experiencing the force. So this one will be by the ground. Okay, previously it's called floor, but since you don't want to mess up the F, there's an F inside in the free body diagram already. So we use G to represent ground, and this is exerted on B. By the ground, on box B. Okay, this one will be by box A on box B. So by box A on box B. Okay, by on. By first, then on. It's never on by. Okay, it depends on which book you follow. But if you follow my class, it's always by and on. If you follow other lecturers, it might be on and by. It depends on which book we follow. Okay, so now we have drawn the free body diagram for both situations. Let's label this one is box B. So now we know the situation already. Let's look at what the question asks for. The question asks for the magnitude of the force that box A exerts on box B. So who is the one experiencing the force? The one experiencing the force is box B. So we have to look inside the free body diagram of box B. Okay, this one is the forces acting on box A. This one is the forces acting on box B. On box B. So look at free body diagram for box B. Who is exerting the force? Box A. So this is exerted by ground, this is exerted by earth, this is exerted by box A. So this is the force that we are interested in. It's by A on B. So we are interested to know what is the magnitude of this normal force over here. So that's our aim for this question. So how do we solve this question? We have to use Newton's third law and a bit of Newton's second law as well. Okay, so there's a few things that you need to know when you look at this question. First thing is, these two boxes are in contact with each other. Okay, this in contact with each other will be a very important information. So let's write it down. Boxes A and B. Okay, I'm going to write in a non-grammatical way because I'm in a rush. In contact. Okay, then then you need to know Newton's third law, but that one we don't need to write. Okay, so let's start. We will analyze box A first, then we'll move on to analyze box B. But which dimension should we analyze for box A? There's forces happening in the X dimension, there's forces happening in the Y dimension. But as you can see, this force that we are interested in is in the X dimension, so probably we should analyze the X dimension first. Then only after that, if there's any issue, there's a need for us to go for Y dimension, only we'll go for Y dimension. Okay, so let's start. So let's do it for sum of fx for box A, then equals to 0 or equals to MA. This is the only force acting in the X dimension for box B. So because of that, you know that the net force in the X direction for box B is not 0. It's not 0 because there's no force on the other side to cancel it out. So because you know there's net force over here, so you know that there will be an acceleration happening to box B and the acceleration should be pointing to the right. Okay, then after that, you know that box A and box B are in contact. So if box A and box B are in contact, if box A is accelerating, if you want to keep contact, if box B is accelerating and box A and B want to be in contact, box A have to follow and accelerate at the same rate as well. If box B is accelerating at a higher rate, then you start to break contact with box A anymore. Let's say if box B is accelerating at a higher rate, then box B will travel faster already. If box B travel faster, then they are not in contact anymore. So when you see that box B and box A are in contact, you know that these two boxes should accelerate together. Okay, the acceleration should be the same for box A and box B. And because of that, you know that box A is also accelerating. Okay, so to summarize, we see box B is accelerating because the net force in the x dimension is not equal to 0. So knowing that box B is accelerating, we know that box A must be accelerating as well. Because box B and box A are always in contact, and to be in contact throughout the whole journey, you have to accelerate at the same rate, so you always stay in touch with each other. And since box B and box A are accelerating at the same rate, you know that if this acceleration is pointing to the right, you know that the acceleration over here should be pointing to the right as well. So since there's acceleration over here, there will be net force acting in the x dimension for box A. Therefore, sum of F over here should be equals to ma, not equal to 0, because there's acceleration here. Okay, so ma, AA. Okay, so once we have done that, let's try to solve this problem. Our acceleration should be pointing to the right, because from our discussion just now, it's pointing to the right, because the net force is pointing to the right for box B. And you follow box A, follow box B. Same acceleration, same magnitude, same direction. So our acceleration should be pointing to the right. So we take pointing to the right as the positive x. Okay, so we can write taking to the right as positive x, then you can take F minus NBA, and this is equal to MAAA. Okay, so this is our equation for now. You know that F is equal to 100, MBA you don't know, mass of A is 20.0, AA is this. Okay, so that's all that we know for now. So let's take a break for this box A. Let's move on to box B. Okay, because we are focused on the x dimension, so let's ignore the y dimension for this. Move on to the x dimension for box B. So for box B, we again do the same thing. So we are going to take sum of fx for box B, and this is equals to mass of B, acceleration B. Of course, the net force acting on B should be related to the acceleration of B, right? It shouldn't be the net force of B causes the acceleration in A. It should be on the same body, right? Net force acting on one body should be the acceleration should be equals to mass times acceleration of the body itself. It's supposed to be the same body. So if this is B, this is B, this is A, this is A. Okay, so once you know that, then now we know for this free body diagram, the only force acting this way is NAB. And since it's pointing in the positive direction, it's pointing to the right, so it's positive direction, so it's a positive. If it's pointing to the left, then you need to put negative, because we are taking to the right as positive. Okay, then it's equals to MB AB. So now we don't know NAB is how much, but we know MB is 5.0, and this is AB. Okay, so once we reach here, we are again stuck. But here is something important. Now you know that due to Newton's third law, you know that forces exist in pair. Okay, and there's action-reaction pair. So you know that if A exert a force on B, B will also exert a force on A, and the force should be same magnitude, opposite direction. So if this is the force exerted by B on A, then it should have the same magnitude as the force exerted by A on B. So this NBA and this NAB here is actually an action-reaction pair. So this is A on B, this is B on A. So they form a pair. So you know, because they are a pair, they should be opposite direction. This one left, this one right, and they should have the same magnitude. So because it's the same magnitude, we know that this one we can write NBA equals to NAB, and let's just call it N, then you make things simpler. Okay, so this N is the one that you want to find, because this is the N that is exerted by body A, by box A on box B. Okay, we give it a name just that we give it a common name N here, because we don't want later you hesitate whether we should write BA or AB. So we just write it as N. We give it a new name, we call it N. So this N will be the answer that I want to find later. Okay, next thing is we know that because boxes A and B are in contact, because they are touching each other, they have to accelerate together at the same rate, right? If the acceleration for body A is 5 meter per second squared, then acceleration for body B should be the same 5 meter per second squared. If one is larger than the other one, then they will break contact from each other. Then it's not following this situation anymore. So you know that the acceleration for both bodies should be the same. So acceleration for box A should be equals to acceleration for box B. And we'll call it by the common name, acceleration A. Okay, so once we know that, we can shift our equation around. We are interested with the normal, we are not really interested with the A. So let's shift A to be the subject, so we can equate later. So we shift A to become the subject, then it become 100 minus normal force divided by 20.0. This is A. Then this one, the A should be N divided by 5.0. So this one is equation 1, this one is equation 2. So what do we do to these two equations? We equate 1 and 2. Okay, so we equate the 1 and 2 because these are the same A. So what do we get? 100 minus normal force divided by 20.0 is equals to normal force divided by 5.0. And if you move around things, then you find that the normal force is equals to 20 Newton. So that's your answer. The normal force is 20 Newton. And what is the by and on for this normal force? It's exerted by box A on box B. And of course, this normal force is also exerted by box B on box A as well. So this one is 20 Newton, this one is also 20 Newton. Just what this one is 20 Newton to the left, this one is 20 Newton to the right. Together they form an action-reaction pair, equal magnitude, opposite direction. So that's all for this question.